And yeah, it's a pleasure to be here. And so today I'm going to speak about some work we have been doing really in the agricultural field. So I'll give you some example of the type of project that we've been running, and this is something that I've been doing with my collaborator Peter Kopitke at the University of Queensland. So as we heard this morning and also yesterday, agricultural challenges are often a problem of scale. So you can approach them at one end of the scale or at the end of the scale. Today, because it's an agricultural workshop, I'll speak about the right side. Is there, you cannot see yep. So I will speak mainly about the right side of the scale. And why can we do this? Okay. Yeah. We can do this because in the last 10 years we had an incredible development in terms of synchrotron capabilities, especially in terms of detectors. So in terms of X-ray microscopy, for instance, about 10 years ago we had the Maya detector that came online, and all of a sudden we went from collecting 1 pixel per second to collecting 1 pixel in a millisecond. So basically overnight we went 1,000 times faster, which means that if you now do an experiment that lasts 1 day with the Maya detector, it would have taken you 3 years to do the same experiment before. And I love spending time with the synchrotron, but beam time of 3 years, probably I would have passed on that. The other thing that we did, of course, is using fly mode instead of step scan. And these days, this kind of time domains are common not just to the Maya detector. Now with fast electronic and on the silicon drift detector, basically most of the good beam line now can access this type of time, which means that we can do experiment we couldn't do just 15 years ago. So it's now over 10 years ago, we did the first tomography in fluorescence of live roots. And then a few years later, we did the first experiment on live plant. So where in this case, we were looking at the absorption of foliar fertilizers. And these are exactly the same leaves scanned, after 24 and 48 hours. And, the plants was living in hydroponic even while scanning. And so you can do this time series in vivo system. And of course, as we heard yesterday, we can do in vivo CNC imaging again to have a speciation mapping, if you want, using these fast techniques, but again with in vivo system. So today, all this stuff is published, and today I'm going to speak about a project that we started about 2 years ago, and is funded by the Grain Research and Development Corporation in Australia. So it's very much agriculture because they get money from levies from farmers. And so we have to guarantee a return to farmers. The GRDC spends about $200 million a year in field trials, and they do basically bulk measurement. They don't do anything else. There are hundreds and hundreds of field trials every year. But really, what is missing is really a mechanistic understanding of what happened at field scale. And so the GRDC has given us, 3 postdocs for 4 years to develop approach and techniques to actually take synchrotron techniques at the field scale. And so I'm going to speak about 3 areas that we have been working. One related to phosphorus. We have heard this morning how phosphorus is a critical element. It's critical because the resources are running out, but mainly because the resources are geopolitically challenging. 75% of phosphorus is in one country in North Africa, in Morocco. And also the phosphorus use efficiency is abysmal. It's 5 to 25%. So most of the phosphorus end up in water bodies causing eutrophication, and that's why we are exceeding for phosphorus the planetary boundary for this element. That's in part because all our understanding of what happens in phosphorus in soil is from really biochemistry. We have never looked into detail at a spatial resolution level what's happened in the terms of phosphorus chemistry in the soil. But when we apply a phosphorus fertilizer, we have tremendous gradient from the fertilizer itself through the soil. So you go from, percent level of the fertilizer to maybe background level just a few millimeters away. So there are very strong chemical and physical gradients that control the dynamic of phosphorus, which we don't understand. So one techniques to use to look at phosphorus availability that has been employed successfully to predict response to phosphorus fertilization is called DGT. It's a very simple device. There are various layers here. There is mainly a diffusion layer, which is a nitrogen, and then a binding layer on the back that absorb and act as a zero sink for phosphorus. So it mimics the plants in terms of uptake, in the way that phosphorus gets depleted in the solution and gets resupplied from the solid phase. This is again a bulk technique, and what we wanted to do here is develop a technique that we can use at field scale. And so we wanted to develop an efficient way to change this technique and make it possible to be used at field scale using synchrotron. There are a few challenges when you do this. So first of all, zirconium oxide is what is used for absorption of phosphorus. Phosphorus is a really tricky element. Is just over 2 kiloelectron volt. Is in the tender X-ray region. Not too many beam lines that really specialize on that energy range. It's also got a lot of overlap. So zirconium is out because the L edge of zirconium overlap the K edge of phosphorus. Is also a system that uses the resin embedded in a gel. And if you look here, just 10 micron of a gel in which the resin is embedded absorb 40% of the fluorescence. So you cannot actually embed the resin in a gel. And also the conventional binding layers are very tricky to use. They are 95% water. Using them in the field is not simple. So we redesigned them completely. We got rid of the gel completely. And of course, your best friend at the synchrotron is Kapton. And so instead of using a gel, we use Kapton with an acrylic adhesive. You cannot use silicon because then you have the silicon K alpha that is creating havoc on your phosphorus signal. But you can use this acrylic adhesive and you can make your binding layer that is very, very simple. It's just a film of Kapton with your adhesive. You put titanium dioxide as sorbing agent, and you can have this now these DGTs that can be any size. We can do them, up to 20 centimeter in size, and they work very well. So here on the left, there is the what you get in terms of the distribution of phosphorus from polyurethane gels, which is the traditional way or the most advanced way to do DGT. And you can see that, basically we apply a phosphorus fertilizer in the center. And what you expect is something like this, the diffusion from the phosphorus fertilizer granule into the soil. With the polyurethane gels, what you get is an artifact. It's an artifact of the deposition of the binding layer at different level through the thickness of the gel. So with the Kapton system, now we have the diffusion parameters that we expect. Yesterday, I think Jorge was asking about quantitation. So in this case, we also compare the results from XFM with laser ablation SPMS, and you can see they are basically identical. So the data from XFM on the left and the laser ablation on the right, on the same samples. We also do the analysis in a different way. Again, yesterday people were asking about what kind of program you can use. There are a lot of programs out there, beam lines, but when you extract your data, then you can use ImageJ for data analysis. And ImageJ is something like, it's a bit like R for statistician. It's an open source. There are a lot of plugs in. There is a lot of stuff that you can do. In this case, we were using, instead of using the usual, transect or line scan, virtual line scan that you do, you can analyze where is the center or the highest concentration in your figure, and you can extract the radial distance, which means that you use all the points in the map, and so you use 200,000 points in this case to generate those kind of graphs. So it works very well, and we can see difference in performance of different fertilizer in different soils, and some of them are quite surprising. Farmers sometimes don't want to use monoammonium phosphate in calcareous soil because it's a very low pH reaction, is about 3.5, and what you do in calcareous soil is that you just dissolve more carbonates and you make available more calcium that then precipitate with your phosphate. So it's actually counterintuitive, but fertilizer with a high pH works better in a calcareous soil than the fertilizer with a low pH. So we start to get this kind of information and then help us to understand better what is the chemistry that controls phosphorus availability at the microscale in 2D. And then what we did very recently, so 2 weeks ago we collect the samples, last week we analyzed them. We went to actually deploy DGT devices in the field, so we 3D printed this little system where we can then install directly in the field with the plants growing, and then we get then the 2D distribution of phosphorus availability from a field experiment, and that's a biochar phosphate fertilizer in comparison to a conventional fertilizer, and you can see the higher availability of phosphorus there that explain the response that we see in the field. So that's taking our techniques very much from bulk analysis in the lab to spatially resolved analysis in the field. Can be done efficiently, you know. I'm sure that some of you have thought, well, do you really need to use a synchrotron to analyze just phosphorus on a piece of Kapton? And that's a good question. There is a lot of pressure for beam lines. So what we did is actually use a tandem system. And we are very fortunate at the Australian Synchrotron because we don't have one Maya. We have two Maya detectors in the hatch. So there is one over here, and there is one down here. This is on a milliprobe, which is about, sample stage is about a meter in size, so we can put up all our gel there. And what we do is that we reutilize the photons. What we don't do very well, you know, we say every photon counts at the synchrotron. In fact, we throw away an awful lot of very, very useful second-hand photons. And so we put our gel upstream, and then we run a second experiment at the same time downstream. So we use the two Maya detectors at the same time, and we work on two completely independent experiments. One at a resolution of tens of microns upstream, and one with a KB mirror at a resolution of 1 micron downstream. And so you can see here, that's very, very busy, but it's very busy because you have up here you have two Maya detectors that are working. You have two images that are creating online, and the two spectrum down here. And so, we have also proven that there is no deterioration in the signal. So this is the downstream sample, and you can see that independently of whether you have a gel or not, you get the same kind of information. And we use Siemens stars as well to look at the deterioration in the resolution, and you really don't have anything that is significant. So in this way, we can actually do the analysis for free. We can run an experiment downstream and at the same time scanning our gels upstream. The second experiment is about soil constraints and amelioration practices. So about 75% of Australian soils have some sort of constraints, either pH, compaction, deficiency, acidity, salinity, etc. And there's a lot of work done to ameliorate these constraints, but of course there is also a very poor understanding of how they work. And of course one good way to do it is tomography, and we heard about tomography quite a bit. We haven't seen too many examples, and that's because it's really, really hard to do. Tomography of live plants in a decent size soil core, especially taken from the field, which is dishomogeneous, is really hard to do. And most of the studies are done actually on laboratory systems. But, of course, the synchrotron, we have a better source of life. We can use monochromatic beam, so we don't have beam hardening that we have with conventional lab scale systems. And this is the sort of information you get with with one of those lab systems. You can see these are plants grown in cylinders of 3 centimeters in diameter and a resolution of 68 micron voxels. At the Australian Synchrotron, we have a very nice imaging medical beam line. So it has a very, very, very large beam. So the beam is down here. So it's about 2.5 centimeters in height and about 40 centimeters in width. And then we can put our soil cores on the robot and scan them while the plants are growing in there. It takes about 2.5 to 3 hours for our core down to 40 centimeters. So we use cores typically about 10 centimeters by 40 centimeters in size. And that's the sort of information you can get. Again, these are 9 centimeters across, 35 centimeters in length, 34 micrometer voxel resolution. And it takes about 3.5 hours to collect, and it takes about 3.5 weeks to analyze, because it's really painful. You know, just doing the segmentation of these things is painful. If you can do it, so you get quite nice result. Let's see if this one works. So that's the soil core. Of course, it looks quite dense, but you can, of course, filter out most of things. Even so, it's very difficult because you have solid, you have water, you have porosity, and so on. This is the root structure. In blue are the granular fertilizer, and you can see the proliferation of the small roots near the fertilizer, and that's a well-known phenomenon. And then, of course, you can get all the data information about the distribution, and this is color coding the roots of different sizes. So you can extract a lot of information from images like this one, quantitative information, to better understand the sort of treatment that you're using in the field again. What we're also doing, we started a little project to go away from the computationally intensive way to segment these large cores. And use more machine learning. So that was the very first attempt. So supercomputer on the left, laptop on the right. Still a long way from getting a good results, but hopefully we can then analyze this very, very large data set much quicker. The last part of the talk is about cereals, and we heard all about the need to increase the micronutrient content of cereals because of the issues that we have in terms of deficiency in people, and the fact that cereals are a poor source of nutrients. As Mary Lou said before, it's very, very painful to screen libraries of seeds when you need to have 100,000 analysis to get one decent mutant. So this is not really my idea. It was something that was published already in 2006. There was a paper that was on high throughput determination of metal concentration in all index Arabidopsis thaliana seeds using XFM. This was 2006, was not 30 years ago. But you can see that what they were doing was a step size of 100 microns. The Arabidopsis seeds are really small, so you don't get too many pixels there. And 10 seconds per pixel. Okay, and that was called high throughput. So I was preparing a manuscript back then, and I just saw this paper, and I was at the Synchrotron and said, I'll give it a go. So I took 5 seeds of wheat, put them in front of the Marion detector, and that's what you get in 8 minutes without optimizing the system. So in the last few years, we have used this system to do high throughput screening. And so this is a 3 days experiment. We did analysis of over 4,000 EMS mutagenized rice seeds and 533 different rice accession. You end up with a lot of data, I can tell you, a lot of data. And so we have devised a pipeline, an analytical pipeline, again in ImageJ, and is available on this has just been published in New Phytologist. And it takes probably, maybe there are 12 steps to do, but it takes basically half an hour to extract the data from about 500 seeds. Now we have a Python pipeline that really can be used and just give you the results basically straight away. More recently, we have moved into looking at wheat for the same reason, looking at iron and zinc. So this is a nice data set. We use 337 bright wheat genotypes, all grown on the same soil and the same condition with the same fertilizer regime and so on. And in this case, we also look how many replicates you need to have good something that is meaningful. Just using one seed is probably not enough, but how many replicates do you need? And we found that with 3 replicates, basically you can get concentration that are equal to the bulk concentration in a bunch of seeds. And this takes 2 days of beam times. So that's the sort of data that you get. But this is also the quantification that we're getting, which is pretty good, I think. That's XFM versus ICP-MS. So we take 180 of those seeds, and we did single seed digestion, and then analysis with the ICP-MS. It's painful, but you need to build up this sort of data sets. Do the quantification on whole seeds by XFM is really complicated because, of course, they are big 3D objects. You have a lot of physics in terms of absorption, self-absorption within the seed. You have geometry and so on. The XFM quantification is based on the fact that, the assumption is that you have a constant thickness and you have a homogeneous composition, and that's something you don't have in the seeds. So we are quite happy to get already with GeoPixie that kind of quantification, but of course there is space for improvement, and that's what we are doing at the moment, is actually refining those quantifications. And there is a lot of information that we can use, because at the same time as we collect the fluorescence signal, we get also the Compton signal. And the Compton will tell us, what is the size, what is the density, what is the shape. So we can use all this information per each seed to refine the concentration. And that's before we get the distribution of zinc. So there is already all the other information related to the distribution that we haven't even touched, but there is a lot of information that you can extract. And the other nice thing is that you can take the seed that you have used at the synchrotron, you can grow the plants, and we have regrown plants without any damage from the seeds that we analyzed. And of course, I had to put this one up for Mary Lou. This is what you do with Arabidopsis. You can scan a little bit finer, but again, this one takes just a few hours, and you get a decent amount of information, and get you can at least looking at a different mutant and get probably concentration from small seeds. I think the quantification would be easier to do then as a pre-screening. So in conclusion, the progress with synchrotron techniques really allows us to bridge the gap between the spatial resolution and the field relevance. So now we can move toward the field relevance in an easier way. We have proven that tandem analysis can be done at XFM. In fact, I think it should be done also. We already do it at XAS. We always collect the spectrum from a foil downstream of our sample. But we still probably can have another set of samples just after the first one, and probably collect still very nice spectrum. I know there is if the samples are right and are diluted enough and so on, you probably can do that. It's probably cheaper than build another beam line, really. And for XFM, definitely it works pretty well if you have the right samples to analyze. And then computer tomography, of course, is very promising, but the data analysis is really a bottleneck. It is really extremely painful to do it. So everybody speaks about doing it, but actually, if you look out there, there are about only a couple of papers that use synchrotron radiation to do tomography of intact root system on living plants in soil. And then the high throughput screening is actually quite fun to do. So I'll stop it there. Of course, we have a lot of collaborators around the place, at the Australian Synchrotron, of course, and then the University of Queensland for the various projects, and also a person here at Cornell that is involved in our WIT project. So thank you for your attention.